Yes, students. So today, day 6, and one of the biggest chapter we are going to discuss today, and that is rotational motion. Rotational motion. Okay. And rotational motion, we are starting with what? Moment of inertia. Very important from this chapter's point of view. Okay. The moment of inertia means what? Inertia of an object for change in state of rotatory motion. Change in state of rotatory motion. That means it's same as law of inertia only. There is no difference at all. In law of inertia, what we said, inertia is that property of the object or a mass which opposes the change of state. Okay, if the body is at rest, it wants to be at rest. If the body is in motion, it wants to be in the motion. Right, same here also. But here, motion is rotatory motion. If the body is at rest, still it wants to be at rest only. Okay, if you want to put it in motion, you have to apply torque here. Right, if the body is already in rotatory motion, to stop it, you have to apply the torque. Okay, so inability of a body to start its own motion, we call it as inertia. So here we are calling it as moment of inertia, inertia of an object for change in state of rotatory motion. Said okay, fine. Now how to define it, what it depends on? Like inertia, normally we said that it depends on mass. Moment of inertia depends on what? Moment of inertia depends on distribution of mass around axis of rotation. Okay, and we represent it with I. Moment of inertia we are representing with I. It depends on distribution of mass. Distribution of mass around axis of rotation. Around axis of rotation. Right? Okay. Then what is the formula? Formula we will be seeing here. What we can do? Take one axis. Right? And in this one, suppose we have mass m1, this is r1. Then we will say that moment of inertia of this is m1 r1 square. Okay, the formula for this is mr square or m1 r1 square. If there are multiple particles, add it. Okay, then you will say that is okay. m2 r2 square. If there are more like this, then we will keep on adding them. Correct? So what you can say? Sigma mi ri square. This is I equal to 1 and I equal to n if there are n particles like this. So I equal to sigma of mi ri square. This is moment of inertia. Right? What is its unit? Unit is kg meter square. What type of physical quantity, vector or scalar? Actually neither vector nor scalar. Actually is tensor quantity. Tensor quantity. But if suppose the question is coming and in that one tensor is not there, then we will go for scalar. Okay? If in options tensor is not mentioned, in that case our answer is scalar. Our answer is scalar quantity. Scalar quantity. Okay, in that case our answer is scalar quantity. Is that right? Okay. Now let's find out. Let's do a question or two on this one. Suppose that we have two particles here. Okay, m1 and m2, and separation between them is r. Okay, and we have to find moment of inertia about an axis passing through the center of mass. We have to find moment of inertia to an axis which is passing through the center of mass. Maybe center of mass, let's assume it's here. Okay, the center of mass. So what is the moment of inertia about this axis? So okay, fine. Moment of inertia's value we know. Yes, we know what is moment of inertia in that case. If suppose I take, which one shall I take? 0. Yeah. Okay, then let's assume this is x. So what is x value then? X value you can write m1 r by m1 plus m2. That is only no. m2 into 0, m1 into r by m1 plus m2. That's what we have learned in moment of inertia. So x value is m1r by m1 plus m2. Then moment of inertia. Moment of inertia will say m1 to r minus x whole square plus m2 to x. Correct. So m1 into r minus this, r minus m1r by m1 plus m2 whole square plus m2 into m1r by m1 plus m2 whole square. Correct. Now what is this? Take its LCM. m1r will get cancelled. It will be m1 into m2r by m1 plus m2 whole square plus m2 to m1r by m1 plus m2 whole square. Now in this one what we can take common? You can see that here is m1, m2, r by m1, here r square by m1 plus m2 is fully common. So what I am going to do is just check m1, m2, r square by m1 plus m2 whole square. Now what is that? Now it is m1 plus m2. Okay, so this one and this one gets cancelled. So what we are getting? We are getting m1, m2 by m1 plus m2 into r square. This is moment of inertia about center of mass. m1, m2 by m1 plus m2 r square, and this is the least moment of inertia of these two particles. Okay, moment of inertia about center of mass is least. Remember that. Moment of inertia about center of mass is least moment of inertia of system. Okay, I hope it's clear. Any doubt is there in this one? Students, any doubt? No problem?
Sir,
Yes.
when you say the derivations of the M1 R minus M1 R by M1 by M2
Then what happened? Take no LCM.
Okay.
M1R plus M2R, multiply here. M1R plus M2R minus M1R by M1 plus M2. So M1R gets cancelled. What is there? This will come. And this you should remember. Like x value is M1R by M1 plus M2, this value will be M2R by M1 plus M2. So you should remember. Then only it will be R. No, this plus this is what? R only, right? So you should remember that. Okay, so this is M2R by M1 plus M2. Here is M1R by M1 plus M2. Solve it. You will be getting M1 M2 by M1 plus M2 R square. Remember this also. This is important. Moment of inertia about center of mass of two particle system, and this moment of inertia is least. Okay, so this is least for two particle system. That okay, fine. Then, so we said that moment of inertia depends on how distribution of masses. That means is this. If suppose this is an axis of rotation. Now here I have 2 kg. Okay, and this is at a distance, let's say by 1 centimeter. And another system is there This is axis of rotation, and same 2 kg now is somewhere here. And this is maybe 3 centimeter. So whose moment of inertia is more? Here. This is system 1, this is system 2. Now what we change? Is the mass changed? No. Is the axis of rotation changed? No. Then what is changed? Mass has gone far. So its moment of inertia is more than moment of inertia of this. I2 is more than I1. So what has changed? Distribution of mass. Mass has gone farther. If the mass has gone farther, moment of inertia increased. That means inertia has increased. It is tough to start motion for this one. It is tough to not start. Tough to start and tough to stop. Okay, because its moment of inertia is more. So it depends on distribution of mass as well as sometimes you will see that position of the axis also. Position of axis how? I'll just explain you a little later. Okay. So this is how we can calculate moment of inertia. Now there are certain bodies, rigid bodies, whose moment of inertia, what is the value we should remember. Standard those moment of inertia. Okay. So MI of uniform objects. We must remember that. Okay, so first one we go for rod. Okay, rod is here. Length is L, mass is M. Okay, so moment of inertia about its center of mass. Moment of inertia about its center of mass. Okay, so what it is? It is standard value. So ICOM is ml square by 12. ml square by 12. We should remember. Second, ring. Ring. Now in ring, about which axis? This is ring. Okay, about which axis we are saying? An axis which is passing through its center and is perpendicular to plane. Means like this. This is the axis. Passing through center and perpendicular to plane. This and this are same. Okay. As this is radius r and mass m. Same thing here. Radius r and mass m. If I say this is, at the moment, if I say this is z axis, and this is z axis. Okay, this is perpendicular to the plane. In this one, if I show you x and y axis, where are x and y axis? This is x axis. X axis here. Okay, this is x. And then where is y? Y is here. This is y. You can make it with more colorful. I think it will be better for you if you can see that in colors. This is here. And z axis also. Leave it. Z is fine. So x, y, and z. Okay. So y and x axis are what? These are the axis of the plane. Axis of the plane of the ring. These two axes are in the plane of the ring. Like suppose my hand is there. This is my hand. Okay. Now, any plane, this is plane, 2 dimensional. Okay. 2 axes are required to define that one. Now, this is x axis, this pen. If I am keeping it like this is x axis. Okay. And this is y axis. These are axes of the plane itself. X and y. Perpendicular to plane means this. This is perpendicular to plane. This is z. Okay. This is z, x, y. Same thing I have made over here. Clear? So about Iz, about this Iz, we have its moment of inertia as mr square. right? This we should remember. Then disk, same way, exactly same way. Can make it over here. Disk is there, and disk if we make, this is disk, okay. This is your disk. Now here also Z, same way we can define it. Okay, two axes are there which are in the plane. So two axes of the plane are like this. This is one. You can say this is the x axis here. Another one. This is y axis. Okay, both are there, x axis as well as y axis. We can see that clearly. Then what we are defining? Iz we are defining. What will be Iz? M r square by 2. This is r and its mass is m. Where is z axis? I can't show you in this one. Then again we have to make it like this to show z axis. Okay. If you want to see, I will show you one more time. This is your disk. Okay. This is disk. And where is z axis? This is z axis. Okay, you will say that, okay, this looks like y axis only, then why it is z? You have to see the orientation to understand that. Okay, this is y, this is x, but here this is z. And where is x and y? This is x. This is x axis. Then where is y? Y is this here. This is y. Okay, so z axis means perpendicular to plane. And what is the moment of inertia? Mr square by 2. Right? Okay. So rod, ring, disc. Okay, then sphere. Solid sphere different, hollow sphere different. Now in case of solid sphere, about any axis or hollow sphere also, any axis is there, x, y, z, whatever you take. Same moment of inertia for all. Okay, same moment of inertia, whichever you take. If the axis is passing through the center, then moment of inertia is 2 by 5 mr square for solid sphere. And for hollow sphere, 2 by 3 mr square. Okay, this is for these round objects. 4 round objects we saw. This is moment of inertia. This is sphere. Then, what is necessary for us to know? Cylinder. Okay, cylinder is there. In cylinder, what is there? Suppose we are taking cylinder like this. Okay, this is our cylinder. And axis is passing through the axis of the cylinder itself, like this. Then what is moment of inertia? Mass is m, we will take, radius is r. Two cases possible, one is hollow cylinder. So hollow cylinder's moment of inertia will be similar to ring. So here it will be mr square only. Solid cylinder, mr square by 2, like disc. Okay, these are all standard values we have to remember, there is no choice. Okay, then after this what? After this we'll use, okay, let's find it out, then we'll use it later. Okay, plates. Suppose we have a rectangular plate. Okay, so rectangular plate, we can make here something like this it is. And I want to know moment of inertia about an axis like this, maybe x axis here, okay, which is passing through the center. So x, mass is m. Okay, this length is a and this length is b. So moment of inertia about this Ix is mb square by 12. This very similar to rod. Okay, very similar to rod it is. It's passing through the center. So if I consider this as the length, so mass into b square by 12. Now same way, if another axis which is passing through its center, but it is along y-axis like this. Okay, this is y. So Iy is ma square by 12. Okay, ma square by 12. How these are coming? How we are finding moment of inertia of uniform bodies? It's integration, obviously. And what is the formula for that? dm, that means the small particle, small mass that we are considering, into square of the distance from axis of rotation. Integration of this. This is the formula. From there only these values are coming that we are writing at the moment. But that's not important. Questions are never asked on this, how this came. Questions are asked for usage of them, because these usage we have to do to find out moment of inertia of certain other things. Okay, so this is mb square by 12, ma square by 12. Then what more? Anything more is there? Yes, triangle also you remember. For triangle, what we have? Suppose this triangle we are taking, right angle triangle. This is height h, mass is m, and we want to find moment of inertia about its base. Okay, about base. So what will be a moment of inertia about this axis? We'll say mh square by 6. mh square by 6. This we have to remember. Okay. So these are standard moment of inertia which we have to remember. Now what then? After this? After this we are going to see parallel axis theorem and perpendicular axis theorem. Parallel axis theorem first. And the questions will be based on these two theorems only, if at all the questions on moment of inertia is asked from us. Okay. What is parallel axis theorem? Parallel axis theorem says, if we want to know moment of inertia of any object about an axis which is parallel to an axis passing through center of mass. Okay, suppose I take one object over here. Let's say let it be a ring. Okay, so this is ring here, and this is the axis passing through its center. Okay, this axis passing through its center, and we want to find out moment of inertia about another one. Okay, another one which is parallel to this. Suppose somewhere. Okay, so parallel axis theorem says what? Parallel axis theorem says, if we want to find moment of inertia about an axis which is parallel to moment of inertia, rather parallel to an axis which is passing through center of mass, then it is equal to IAB is equal to moment of inertia of object about an axis passing through center of mass plus mass of the body. Mass of the body is m into distance of square of the distance between two axes. So mr square. IAB equal to ICOM plus mr square. Okay. Can we apply this on any object? Yes, this can be applied on any object. This theorem is applicable everywhere. Applicable for all objects. This is applicable for all objects. Okay, IAB equal to ICOM plus mr square. Suppose now this itself is a question, and we want to find that what is IAB really. Then IAB actually is, now we know that this is what? This is ring we have said. So let's write this is the ring. So what is moment of inertia about the center of mass? We know it's mr square because this axis is perpendicular to the plane. So mr square plus m square of the distance between them. Now this is smaller I have written, but actually how much it is? Capital R. So small r equal to capital R, we'll write over here. So what is moment of inertia? It's a 2mr square. So IAB equal to 2mr square. Okay. Now, if suppose this axis, one more axis we make here, and that axis is somewhere somewhere here. Okay, and this axis we are saying, let's say this is Mn. This axis is Mn. And this distance is r by 2. Now what will be the moment of inertia about Mn? Say Imn equal to ICOM plus m x square. What is x here? X is r by 2. So right here mr square plus m into r by 2 whole square, that is mr square by 4. So answer will come 5 by 4 mr square. Okay, same thing we'll do in rod's case, because rod is also having one more standard value. What is that? Let's see. So if we are taking rod, okay, suppose this is rod here, and I want to find moment of inertia about an axis which is passing through its end, like this. Okay, I want to know moment of inertia about this axis AB. Mass of the rod is m and length is L. Length we can take as L. Right. So what to do? This, about this I know. Okay. But do I know its moment of inertia about its center of mass? Answer is yes, we know that. This is center of mass over here. And we know what is moment of inertia about this. What it is? Standard, it is ml square by 12. Now, what is the distance between them? That also we know. It's L by 2. Right? This is L by 2. So, what will be IAB? IAB is I center of mass plus mx square. What is x here? L by 2. So, ml square by 12 plus m. L by 2 whole square means ml square by 4. Answer is ml square by 3. Standard. We should remember that. Okay. Same way, suppose somewhere else we have to find. No issues. We can do it somewhere else also. Let's take somewhere here. Okay. And this we'll say is Mn. And the distance between them, separation, let's say, is this separation. What happened? Some problem. Okay, we'll make it. Right. So now this is maybe L by 2 again. Not L by 2. Not possible L by 2. Take it as L by 4. So I about Mn is what? Imn, same formula, ICOM plus mx square. So this is ml square by 12 plus m L by 4 whole square, that is L square by 16. This will come 48. So 4 ml square plus 3 ml square. Answer 7 ml square by 40. Based on this, many questions are there. Okay, use of parallel axis theorem. Many questions are there. Okay, so this is how we have to use parallel axis theorem. First, we should know what is the moment of inertia about center of mass, and then we can apply this. Right, now let's see perpendicular axis theorem then. Okay, so perpendicular axis theorem is what? Now this you cannot apply everywhere. This is not applicable on every object. This is only for two-dimensional objects. Only for 2D objects. Okay, what it says, Again, I am making one ring. Okay, so that I can show you all the x's one more time. Okay. So in this one, first let's make this is one axis. Okay, then this is another one, and then the third one. Okay, all the three axes I have made. Then this is x-axis, this is y-axis, and this is z-axis. Okay, which is perpendicular to the plane? Z-axis is perpendicular to plane. So what axis says? Moment of inertia about z-axis of this body. Now all three axes are passing through that center. Remember that always. Okay. So Iz is equal to Ix plus Iy. Iz is equal to Ix plus Iy. This is perpendicular axis theorem, where we have to apply in two-dimensional objects. That means you can apply it in ring, you can apply it in disc, you can apply it in plates. Okay, but you cannot apply this in sphere. Not possible. Okay, you can only apply in two-dimensional objects. So Iz equal to Ix plus Iy. So let's see, if you are talking about a ring, this is the ring only. Let's say its mass is m, radius is r. So what I will do is, first of all, this ring I will make like this also. Okay. Now in this one, this is x-axis and this is y-axis. Okay. This is x and this is y. And where is z? Z is perpendicular to the plane. Okay. Now when we talk about a ring, in the ring we know that moment of inertia is mr square. But about which axis? Perpendicular to the plane. That means about z. Okay. So in ring, Iz we know it is mr square. But now I want to know what is moment of inertia of the same ring about x-axis or y-axis. Perpendicular axis theorem I know. I want to use it and I want to get Ix and Iy. What I can do? Now moment of inertia is what? Inertia which depends on mass distribution. Okay. So see now, Ix about this axis. What this axis is doing? It's dividing the ring into two equal parts. Two equal parts. Okay. What about y-axis? Y-axis is also dividing the ring into equal parts. Is the distribution along y-axis and distribution along x-axis is similar? Exactly similar. Exactly similar. Because x-axis also, if you rotate by 90 degrees, y-axis no. Correct or not? So, distribution about x-axis is exactly same as y-axis. So, that means we can say Ix equal to Iy. Yes, absolutely we can say. If that's so, then we'll put here Iz is mr square and here I can write 2Ix. So, Ix value comes out to be mr square by 2. That means y also. Right. So, we can find out what is the moment of inertia about x-axis also. What we were knowing earlier about z. But now we can find it about x and y also with the help of perpendicular axis theorem. So, if that is so, then we can also find moment of inertia about this axis, which is passing like this. Answer is yes, why not? If this we have to find and we say that this is AB, then about AB also we can find the moment of inertia. Earlier we were not able to find, but now we can. How? Because I can write IAB is equal to Ix plus mr square, because this distance is mr square. What I did? I used parallel axis theorem. Because Ix is passing through center of mass only. Right? So IAB equal to Ix plus mr square. Ix is what? Mr square by 2. So mr square by 2 plus mr square. It's 3 by 2 mr square. Right? We can do this without any problem. About if some axis is there here, then we will take Iy. So about any axis now, we can apply parallel axis theorem and we can find about any axis if we know the distance of that particular axis from any axis which is passing through center of mass. Ring, disc, okay, anywhere. Same way now, I am going into the rectangular plate. Rectangular plate already we saw moment of inertia about x-axis and y-axis. Now we want to find about z-axis. So it's a rectangular plate. This is A and this is B. Okay, and we already know what is moment of inertia about x-axis and what is moment of inertia about y-axis. Right? This is x, this is y. About x, we already know it is mb square by 12. And about y, we know it is ma square by 2. What I want now? I want to know about z-axis, which is here. Okay, which is here now. So what to do? Simple, perpendicular axis theorem. What it says? Iz equal to Ix plus Iy. All x, y and z all are passing through the center only. So Iz equal to Ix plus Iy. So what is the answer? M by 12 a square plus b square. That is Iz. This is a moment of inertia of rectangular plate. Now suppose this becomes a square. Square means square of side A. Then what you can say? Iz will be m by 12 a square plus a square. Correct? M by 12 a square plus a square. That means ma square by 6. For the square. Okay, square, we have some more questions. Okay, in the case of square, what questions are there? So square, they ask us, now we know that moment of inertia is ma square by 6 about an axis passing through center and perpendicular to plane, z axis. But they ask you moment of inertia about an axis which is passing through like this. This is diagonal. Okay, what is moment of inertia about this, they ask us. You already know about z-axis. Z-axis is like this, perpendicular to plane. They are asking about AB now. What to do? You will say no problem. There is one more diagonal. That diagonal is like this. Okay. Now the speciality of diagonal of square is that both the diagonals are perpendicular to each other. So means I can say this is x-axis and that is y-axis. What else? We rotated them. This is x-axis, this is y-axis. This we rotated like this. They became this. Still they are dividing this square into two equal parts exactly same way. Yes, both are diagonals. So what will happen? Ix and Iy will be equal. Okay. So again we will write Iz equal to Ix plus Iy with Ix equal to Iy. And this you know already, this is ma square by 6. And this is equal to 2Ix. So Ix value ma square by 2. So about diagonal also the same what we got here. Okay, for square, not for this. In this rectangular they are not going to ask you. Don't worry, this is standard. Okay, so ma square by 12. Fine. If I change the axis one more time in the square only, then if suppose axes are like this is square. Okay, in this one I am making the axis like this, passing through center only, but it's like this. Now I want to find moment of inertia about this. About this also same, because this is also dividing in two equal parts. One more we can have perpendicular to this. Yeah, possible that also. Perpendicular to this, how that will be? Something like this it will be. Perpendicular and passing through center. Okay. something like this. So if this is x-axis, we can say, then this is y-axis here. And this is perpendicular to plane. So IAB again is MA square by 12. Remember that. This is square. Okay. So this way we have to use parallel axis theorem and perpendicular axis theorem to find out moment of inertia of lot many things. Lot many questions are framed and are asked directly in the exam. So we should be able to use these parallel axis theorem and perpendicular axis theorem. Okay, right. Let's move ahead then. This was moment of inertia, the first topic of rotational motion. Second one, what we are going to do? In second one, we'll talk about, let's say, angular velocity. Okay, what is angular velocity? Angular velocity, normally we say if there is a uniform object like ring is there and it is going to rotate about this axis of rotation. Okay, it's rotating. So we say that its angular velocity is omega. This is related to rotation of uniform object. Fine, you can understand that. And what omega is basically? Theta by t. Okay, omega instantaneous, d theta by dt. What is this theta by t? That means rate of change of angular position. Rate of change of angular position. This is change in angular position per unit time. That means how much angle it has rotated per unit time. Okay, theta is angle rotated so omega we can say angle rotated per unit time. In this one understandable how this is rotating like this, how much angle it is rotating per unit time is omega. But there is one more way omega is defined. What is that? It is defined that if suppose that there is a person over here. Okay, in front of that, there is one particle. That particle is moving in this direction with speed v. Okay, after some time, that particle will be somewhere down, maybe here. Okay, but this person, when it is watching him, it's watching like this. So the question is, has the motion of this particle made this to rotate his head or rotate his eyes? Answer is yes. So is the angle changing? Yes. Here it was some angle, here this some angle. That also is omega. This is also omega. Now how to make it, how to measure it? This I know, this is velocity v. So how to measure it? I said okay, at what position you want, because there are two positions. So instantaneous can we measure? Yes, we can measure instantaneously. At this point, if suppose omega is asked from us, then here it is, if suppose I say this is r, then I can say this is v by r, such that r is perpendicular to v. But in this place, what it will be then? Here what it is, because velocity is like this here, and this is not r, something else, maybe x. So how to find this? Always remember omega is v by r perpendicular. What we have to do? I have to find the angle, or I have to find perpendicular component of velocity, which is perpendicular to this x. That is also fine, or I can see its component which is perpendicular to v. That's all our wish. So what I am doing is I am going to take perpendicular component of velocity. So I am going to find this component. Does it look like perpendicular? No. Okay, something like this. So if this is theta, you know this is 90, this is 90 minus theta here. right? And this is 90. Is it 90? Yes. So 90 minus theta, this is 90. Okay, so what this is? This has to be theta. This is V. So this is V cos theta. Okay, so omega here at this point. This point omega is what? This point omega is V cos theta by x. What we did? I found perpendicular component to x and we have written V cos theta by x because omega is V by R perpendicular or V perpendicular by R, whichever way you write it. Okay, omega is V perpendicular by R. Remember, when to use this one? When you are talking about a single particle which is in motion. Okay, then omega is this, V perpendicular by R. Okay, now this is used in many places. Sometimes they'll be asking you this question that there is this rod maybe. Okay, it's one point, let's say, is going with speed V like this, and another one is going with speed 2V like this. Okay, at this angle, what shall I take? 30 degrees. Okay, take 30 degrees. And this angle you take 60 degrees. And this is L. Now what will happen actually? Because their velocity is different. So this is going relatively at less speed, this is going faster speed. So what will happen? It will move like this also, but it is going to turn also. The question will be asked, find its omega, find angular velocity. Then what we are going to do? Very simple. First thing is, this is the length, right? And this only we are going to take R also. So first find perpendicular velocity. Velocity is perpendicular to this L. You'll say, okay, this is V sine 60. And here is 2V sine 30. Now here two particles are not given, not single particles. So here will be relative. Omega will be V relative by R perpendicular or V relative perpendicular by R, whichever. So what we have done already, V perpendicular to that we have found. What do you say? 2V sine 30 minus V sine 60 by R. R means L. That's all. When two particles are given, take relative, but it should be perpendicular to R by what is the separation between them. So what you will write here? 2V sine 30 means V minus root 3 V by 2 by L. So our answer is what? 2V minus root 3V by 2L or V 2 minus root 3 by 2L. This is omega. Okay, so remember relation. Okay, omega and V relation. Now, vectorially what relation is there? Vectorial relation is V equal to omega cross R, not R omega. V equal to omega cross R. So if suppose that omega is given vectorially, R is given vectorially, and he is asking V, do the cross product. We know how to do cross product with the help of determinant. Put it in determinant, find the velocity. Simple question. Okay. If he is giving for a particle which is moving with linear velocity and find omega, this is here. Previous one is here. This one. Okay. So V, R and omega relation. This is angular velocity. Okay. Same way angular acceleration is also there. Okay. So angular acceleration relation is what? Angular acceleration has a relation with tangential acceleration. So if suppose we have a ring, this is a ring, okay, and this ring is having angular acceleration. Now, angular acceleration when it's rotating, okay, so rotating like this is alpha, and this particle here on the circumference, it is having tangential acceleration. Okay, so what is the relation? If radius is r, general relation we write as AT equal to tangential acceleration equal to r. But now, to understand this in more better way, I am going back for omega. Omega's direction is what? Because we said it's a vector quantity. You said no. I told you that V equal to omega cross R. That means omega is a vector quantity. What is the direction of omega? The direction of omega is always perpendicular to the plane. Means, okay, one more time ring I am making. This is the ring. Okay. Now, if this is rotating like this is omega. I mean, rotation is clockwise. So, what is the direction of omega? Direction of omega will be given by thumb. How is the rotation? Clockwise. Clockwise is the rotation. Where is my thumb? Inside. Okay. Clockwise rotation, thumb is inside. So, inside is the direction of omega. Omega is always along the axis of rotation. Remember, omega is always along axis of rotation. That's why it's called axial vector. Okay, this is axial vector. And so far what we have seen, force, velocity, acceleration, those were all polar vectors. This is axial vector. Okay, it's always along axis of rotation. So where it is? Inside. If it is anti-clockwise will be like this. So where will be omega? Outside. Right. So if omega is like this, what about alpha then? Alpha also, this is also tangential acceleration. Alpha is tangential acceleration. So here what rotation I have given? Clockwise. So where is alpha? Inside. Okay. AT equal to R alpha. This is what we normally use. Okay. And alpha is tangential acceleration. Alpha is tangential acceleration. Oh my God. Alpha is what I was trying to say in this one. Angular acceleration alpha is, not tangential acceleration. AT is tangential acceleration. Okay. AT is tangential acceleration. Right. Okay. And alpha is also axial vector. Okay. Now, as we were doing in kinematics, we said that acceleration is positive. It depends on whether it's in the direction of velocity or opposite. If it's in the direction of velocity, we'll take acceleration positive. If it's opposite to the direction of velocity, we'll take it negative. Here also same. Angular acceleration is there. If its direction is same as omega, then it is called acceleration. If its direction is opposite to omega, then it's called retardation. Okay. Fine. So in this one also kinematics is there. Right? Kinematics of circular motion or kinematics of rotation. Kinematics of rotation. So same equation of kinematics are here also. Three equations. Omega final equal to omega initial plus alpha t, v equal to u plus at. Second one, theta equal to omega initial into t plus half alpha t square, and omega final square equal to omega initial square plus 2 alpha theta. Okay, same, and we can find one or two questions we can solve also. Suppose a question is given. A disk rotates at 120 rpm, increases its angular speed or increases its speed to 240 rpm in 6 seconds. Find angular acceleration. And number of rotations made in the process. Okay, a disk rotates at 120 rpm, increases speed to 240 rpm in 6 seconds. Find angular acceleration and number of rotations made in the process. Okay, the first thing is it's given to us in rpm. rpm is rotations per minute, revolutions per minute. 120 revolutions per minute, but we don't have revolutions per minute formula. We know omega. So we have to convert this into radian per second. Omega's unit is radian per second. Correct? So each revolution is actually 2 pi radian. And here it's in minutes. First of all, convert that in seconds. Bring its frequency first. So frequency is in rotation, revolutions per second. So 120 by 60. So it becomes 2 RPS. Now this is frequency. And omega is 2 pi into frequency. That way you remember, better it is. So that means it will be 4 pi radian per second. Second one, this is 240 RPM. So this is omega initial. Omega final will be what? 240. So 240 by 60. 240 by 60 means 4 RPS. 4 RPS, so 2 pi into 4. So it will become 8 pi. So 8 pi radian per second. Omega initial, omega final, both we know, and time is also given. So then what is there? First equation you will use. Omega final equal to omega initial plus alpha t. What is that? 8 pi. 4 pi plus alpha into 6. So alpha value is 4 pi by 6 radian per second square. Second question is number of rotations. How many revolutions you have made? How to find? Second equation. Just find out that how much is the rotation, how much is the angle you have rotated. Third equation also you can do. Omega final you know, omega initial you know, alpha also you know now. Third equation also you can use to find theta, or second equation you can use. It's our wish. So suppose I am using second. So omega initial is what? 4 pi. Time is 6 seconds. Plus half. Alpha 4 pi by 6. Time 6. Okay, so this 6 and this 6 cancelled. Here it is 24 pi. Plus here it is how much? 12 pi. The total is 36 pi radian. The question is asking us this radians. No, question is asking how many revolutions you made. So one revolution equal to 2 pi radian. One revolution is 2 pi radian. So here how much we have turned? 36 pi. 36 pi by 2 pi. 18 revolutions we have made. 18 revolutions we have made. Okay. So this kind of questions also you will find in rotational motion. Okay, which is based on kinematics equations. Okay. Can we write one more equation? Theta turned in nth second. Yes, you can write. You can write. Whatever we have seen in kinematics, we can apply over here by just by changing the variables. Theta in nth second. Distance traveled in nth second. What we said? U plus a by 2 into 2n minus 1. Here also. Omega initial plus alpha by 2 into 2n minus 1. Perfect. No issue in that. Okay, we can use. If the question is asking, I have not seen any question like that, but we can use it. No problem. So now kinematics we applied, we discussed about omega, we discussed about alpha. Then what next? Next we are going to discuss is about angular momentum. Angular momentum, we represent this with L. It's a vector. Which vector? Axial vector. One more time. All the quantities which we are writing with angular velocity, angular acceleration, angular momentum, all are axial vectors. Okay. So what is its formula? General formula for rigid body rotation, uniform body, or rigid body, L is actually equal to I omega. So that means L will be in same direction as omega. Yes, means same direction. L equal to I omega. This is for rigid body formula. But if you are talking about point mass moving with velocity v, because we said already that if a point mass moving with velocity v, still it can have omega, correct? And we said that omega is equal to v by r perpendicular or v perpendicular by r. So point mass moving with velocity v, its angular momentum r cross p. And what is this p? P is linear momentum. Linear momentum. Or you can say r cross mv. What is its unit? From here it is better to see. Kg, meter per second into meter. So unit is kg, meter square per second. From here also you can see omega's unit is what? Radian per second. So kg, meter square per second. Radian we don't write. So kg, meter square per second. Dimensions m, L to the power 2, t to the power minus 1. Okay. So let's see now on this one, let's solve few questions, then we'll move ahead after that. So if we take one coordinate system here, let's say this is y-axis and this is x-axis. Okay, and here is one particle, mass is m, and it's moving. It's moving in this direction. Okay, with velocity v. Okay, and its position here along y-axis, this position. This position is what? This position, this distance, we will say is something like b. Okay. Still it is slightly tilted only. Okay, no issues. So this is v. Okay. We want to know what is this moment of inertia about this point. This is origin. Moment of inertia of this one. This is a particle. So what moment of inertia we are going to have? R cross P. Moment of inertia. Angular momentum. What angular momentum we are going to have? R cross P. Okay. So what to do? First thing is join this point from here. Join it. So let's join. Okay. Let's assume this is R. Okay, and then let's assume this is theta. Correct? Why theta is required? Because this is r cross p, no? Its magnitude is what? Rp sine theta. This is the magnitude. So theta is required. So theta is what? Now theta you can see if I extend this one, theta basically is angle between r and p. Right? It is the angle between r and p. We'll extend it like this. This is theta. So Rp sine theta. Okay. Now see that. Can I write this one in this way? Say P into R sine theta. Obviously we can write. So R sine theta is what? R sine theta is actually this. This. How? You see that this right angle triangle? Okay. Sine theta value is what? Sine theta value is this by R. Suppose this is X. X by R. R sine theta is what? X. And X is what? B. X is what? B. So here L will be what? P into B or MV into B. Okay, here it's coming mv into b. Suppose now the same particle is now here at this position. This is a new position of that. Okay, let's say n. This is m. So a new position, if I am going to join it, then what is going to be angular momentum? It will be same. Why? Why it will be same? Just check. Now this is r1. This is new angle, maybe phi. Velocity is like this. So angle here is phi only. So what is angular momentum here? Angular momentum is r cross p, but this time it is r1. So r1 cross p. Okay. Now r1 sine phi. What is it? Yes. r1 sine phi into p. What is r1 sine phi? This only. Sine phi equal to this by r1. So r1 sine phi will be this again, and this value is b. So it's going to come again mvb. So if the particle is moving in the same direction, same way, right? Angular momentum about a fixed point will be same. Clear? This angular momentum about fixed point will be same. Right? Okay. Remember that this very important question is asked before. So if the same question is coming, we can write it. That angular momentum will be constant. Okay, if it's going parallel, it's not changing the direction. If it changes the direction, it will be different. So about the same point, angular momentum of particle which is moving in same direction with the same momentum, angular momentum is same. Okay, important points, important questions, so we discussed it. Whereas for rigid bodies, what it is? I omega, correct? I omega is L. Okay, so if this also we solve one question. Suppose I am going to take one disk here. This is a disk, and okay, disk it is, then we should fill it. And axis you take, axis passing through the middle. Mass of the disk is 2 kg. Radius is 20 centimeter. Okay, and it's omega. Omega is given to you as, let's say, 20 radian per second. So what is its moment of inertia, and then what is its angular momentum? Find I and then L. Very simple question. So I is what? mr square by 2, and then we'll find L. So this is mr square by 2. So m is 2 kg. 0.2 square by 2. This gets cancelled. Okay, so this is what? 0.04. That's moment of inertia, SI units. Then L is I omega. So L is 0.04 into 20. Answer is 0.8 kg meter square per second, and this is kg meter square. So this way we can calculate angular momentum easily. There is no problem. Okay, but in angular momentum, if questions are coming, it will be more related to the particle only. Okay, see what are a few more important questions. We can associate this with projectile. How? See, here is a projectile like this, we know. This is u, this is theta. Okay, now if I say that find angular momentum of this projectile when it reach highest point, above point of projection. Okay, find angular momentum of projectile when it is at its highest point, about point of projection, about point of projection. Okay, now in this case, you can see that the direction of motion, direction of momentum is changing. Velocity is changing, right? Here it is in this direction, here it is in this direction, here it is in this direction. So its angular momentum here is not constant. It will be changing. We'll find two positions at least we'll find. We are finding at topmost point and we'll find at bottommost point. Right. So at the topmost point, what is its velocity? We know that u cos theta like this. So momentum mu cos theta. Now angular momentum we have to find about this point. Right. This is the point. Now the question is, do I know this angle? Do I know this angle? Yes, I know this angle, but I am not going to calculate that angle. Without that itself we'll solve. Okay. And how to solve that? So what I'll do is I'll just take you back here. Okay, now just try and see what we have written. We said that it is constant MVB. It's constant MVB. Now, MV is actually the momentum which is here. And what is B? B is perpendicular distance of this momentum's direction from axis of rotation. Perpendicular distance means actual distance is this. This is inclined like this. But what we have taken? Only we have taken this. So what is this? This is perpendicular distance. This is perpendicular distance. So momentum is in this direction into perpendicular distance from axis of rotation. Okay, that is only angular momentum. So same thing shall we do here? Obviously same thing we'll do. You can see that momentum is in this direction. Perpendicular distance from this momentum to this point is what? This only. Or otherwise, we again will find, say, okay, this is alpha, this is also alpha. Okay, then in alpha we will say what? Maybe this is x, this is r, right? Then we will say sine alpha equal to x by r. And what is r sine alpha? R sine alpha equal to x. So angular momentum will write mu cos theta. Sorry. One second. Angular momentum will write what? R cross P. What is R? This R. R, because from here you are finding, this is R cross P. What is P? Mu cos theta. Okay. R cross mu cos theta. Okay, cross it is. So cross also we have to change, no? So R into mu cos theta into sine of angle between them. What is angle? What I have taken? Sine alpha. So R sine alpha is what? The R sine alpha is x. R sine alpha is x. That means again what? Mu cos theta into x only, no? Perpendicular distance. So why not remember it directly? Okay. So mu cos theta into x. Now x is what here? Highest point. So what is angular momentum? Angular momentum directly I am writing mu cos theta into highest point u square sine square theta by 2g. Finished. Over. Now if we ask direction, okay, magnitude we have found. Direction is what? See how it's going to rotate it. This is r and this is velocity. So how is the rotation? Clockwise. R cross P, no. So R cross P. Where it is? Inside. Inside is the direction of angular momentum. Now, how is it rotating? Clockwise. Okay. So this is angular momentum when the projectile is at topmost point. Now suppose that the bottommost point is about to hit. Then what? See? If you are going to talk about the bottommost point. Now bottommost point here, what is the speed? Okay. Here speed is both. We know that here speed is what? Here is u cos theta, here is u sin theta. Right. And here also the particle will be having same u. And this is also same theta. So that means this will be u sin theta and this will be u cos theta. Then what will be angular momentum at this point? Very simple this is now. Perpendicular distance about this point and this point. Perpendicular distance is what? Range. But velocity need to be perpendicular to that. What is that perpendicular velocity? U sine theta. So that's it. M u sine theta into range. Done. M u sine theta into u square sine 2 theta by g. Over. Finished. Nothing we did. Only the concept. Only concept. R and V need to be perpendicular to each other. V R. Here also. V R. Perpendicular distance you want. Done. Over. Okay. So these are the important questions they can ask you for just for the finding angular momentum alone. Okay. So this is angular momentum. Then what? Then let's go on to torque. Torque. What is torque? A physical agent which provides rotation to the object. A physical agent. Force is also physical agent. This is also physical agent. Okay, a physical agent that provides rotation. That provides rotational motion. To the object. Rotational motion to the object. What is this? I said torque. We represent this as tau. Tau is actually R cross F. R cross F. You will see that what is R and what is F. R cross F. This is also axial vector. And another formula is there for this torque. Torque is I alpha. So direction of torque will be same as direction of angular acceleration. Torque is equal to I alpha. Just like F equal to ma, force equal to mass. Mass is representing inertia there. So here I is representing inertia. Acceleration, in place of acceleration, alpha is there. And torque equal to I alpha. Its unit is what? Newton meter. Okay, Newton meter. Newton meter was for work also. Force into displacement, but that we call as joule. Here it is Newton meter, but dimensions are same. M L to the power T, T to the power minus 2. Okay, so this is axial vector. Now, what is this R cross F? So if suppose that this is here axis of rotation, and at this point, this is R, you are applying F force. Okay, then what we are trying to create? We are creating torque, or otherwise I should say like this. Okay, we have a rod, this L, and we are applying F force like this. This is R only, right? Don't write L. This R, so that you can rotate it in this way. So R cross F. Here it will become R into F because R cross F means what? R cross F means RF sine theta. Okay, so torque is equal to RF sine theta. Right. So here, what is angle between R and F? It is 90. So we are writing torque is equal to R into F. More the value of R, more the value of torque. If suppose we don't want to increase F, then increase R, and torque value will be more. Clear? So if you have seen that certain when you are trying to open particular screw, if you are not able to open it with it, what you do is you increase its arm. This is called length arm. Increase the length arm, you can open it. Mechanics do it whenever they have to open the tire of truck. You see that they will take very long spanner to open it so that they can increase the torque value, because force is limited. Mg only they can apply maximum. They increase this so that they can open these screws very easily. Okay. So torque is equal to R cross F. Fine. Torque is also equal to I alpha. Okay. Then what we can do? Some questions shall we solve? On torque also. Okay, see. Suppose this is a disk here, and disk I am going to okay. This disk we are fixing from the center. Is fixed. Bring it down. Okay, we have fixed this ring. Disk. This is disk. Okay, and on this disk, its radius and all that we'll define. And this is the radius is okay. Its mass is m. Right now, I am applying force F here, like this. Like this force I am applying on this. So what we have to do is, first thing is find torque, and then alpha. What is torque? What is alpha? So force you are applying like this. So torque is very simple, R cross F. Torque is R cross F. There is no problem in that. But now what is the angle between R and F? Let's say R is this. This is R. This is F. Angle is 90. So torque value is R into F. Second thing, what we have to find? Alpha. What I can write torque is I alpha. So alpha is what? RF by I. Alpha is RF by I. That's it, over. If suppose I also we want to write, we can write mr square by 2. So RF by mr square by 2. R gets cancelled. So 2F by mr. That's alpha. Clear? One more question we can solve. What question is there? Let's see. Okay. One more disk is there. And we fixed it one more time in the same way. Okay. This is fixed. With this one, mass is there. Right? Like this it is now. So what its mass is and its moment of inertia I will give you. Its moment of inertia is I and it's R. What is told to us that we are releasing this. Particle is released. Mass is released. Okay, fine. Angular acceleration of disk. Find angular acceleration of disk. This is the question. Very similar to laws of motion we have solved. Okay. What to do? We'll start with the same way. Same G. T. Acceleration. Here is again T, which is going to give it angular acceleration alpha. Okay, let's write the equations first. Say the mg minus t equal to ma and t into r equal to I alpha. Now, how many unknowns are there in this? T is unknown, A is unknown, alpha is unknown. We have two equations. We can't solve. We require minimum 3 equations. 3 variables, 3 equations. One more equation is required. Now, if its acceleration is A, then what is the acceleration of this point? A. Because this is rotating, that's how it is coming down. If the acceleration is A, then its acceleration is also A. And what is this acceleration? It's a tangential acceleration. So if this is tangential acceleration, and this must be equal to R alpha, that's what we have seen. Right, that is what we have seen. So third equation is this, A equal to R alpha. So what I will do is, this first of all, in place of alpha, I am going to write is just A by R. So this will become I A by R. So tension value is I A by R square. This I am going to put in this one. Okay, so what it will become? Mg minus Ia by r square equal to Ma. Take this one there. So Mg equal to A M plus I by r square. So A value is Mg by M plus I by r square. But we wanted alpha. So alpha is what? This alpha is A by r. No problem. So alpha value is A by r. So we'll write Mg by r into 1 by 1 not M plus I by r square. This is alpha. Okay, like this we can solve a question which is looks like similar to laws of motion but is asked in rotation from us. Okay. Right. So this way these questions are solved, simple torque questions. Okay. Then what else? Relation between torque and angular momentum. Relation between torque and angular momentum. What is the relation? In laws of motion we saw there was a relation between force and momentum. Newton's second law itself is relation. So here also it is there. What is the relation? Torque is equal to rate of change of angular momentum. What it was there? F equal to dP by dt. Here is torque equal to dl by dt, or average value of torque we can write L final minus L initial by delta t, because this is instantaneous, you know that. The average value is this. Okay. So from this one, this is the relation. Okay, we are not changing that one, or we are not discussing this relation much. But if suppose there is no torque, there is no external torque on system. Okay, torque is 0. So if torque is 0, it means dl is 0. Lf minus Li is 0. So if Lf minus Li is 0, what is the meaning of that? That means Lf equal to Li. That means angular momentum is conserved. If external torque is not acting on the system, angular momentum is conserved. If external torque is 0, angular momentum of system is conserved. That means we are going to apply conservation of momentum. If torque external is 0, angular momentum is conserved. What it was in conservation of momentum? If external force is 0 on the system, momentum is conserved. Here, if external torque is 0, angular momentum is conserved. Okay. So students, today's class I am finishing here at angular momentum conservation. We'll start it tomorrow, right? And we'll finish rotational motion tomorrow. Today it's not possible. Still, maybe around 1.5 hour classes left. So we'll do it tomorrow. Okay. So today's practice test I am holding. Tomorrow I'll give you that. Okay. So all right, students. Then see you tomorrow. Bye bye.